In this section, we're going to draw polynomial graphs. That is, we're going to draw graphs from functions. Okay, we're going to use various characteristics of the functions to draw an approximation of a graph. And we're also going to take some graphs and we're going to derive their functions from the graph, as we shall see. All right, so for all graphs in this section, we're going to say that there will be no discontinuities. No jump discontinuities, no infinite discontinuities, no holes. There will also be no sharp corners. Okay. Finally, the domain will be all real numbers. All right. So that restricts this a little bit, but it'll be educational regardless. Okay. So, and we're going to stick with some common graphs. Okay. And by that we mean linear graphs, quadratic, cubic, and quartic. And these are actually increasing degrees of x. Linear is x to the first power, and in general it looks like this. Quadratic is an x squared type graph. In general, looks like this. A cubic, x to the third, in general looks like this. And a quartic graph, x to the fourth, in general looks like this. Okay, we can get to higher degrees, and they will retain many of the characteristics of these, as we shall see. All right, so we're going to stick with these common ones to start out. So first, let's examine the end behavior. That is, what happens at the left and the right ends of the graph. Okay, and for example, let's start with the graph of even degree and one that has a positive leading coefficient. So the highest degree term of x has a positive coefficient, positive 1, positive 2, something like that. All right, the general shape of this graph is going to look like this. It's going to go up at both ends. So therefore, the limit of f of x as x goes to negative infinity, the limit will be positive infinity. It's just going to keep going up as it goes to the left. The limit of the function as x increases to positive infinity will also be positive infinity. Okay, it goes to the right to infinity, it goes up to infinity. Okay. All right. Well, what if if we had a negative leading coefficient? Okay, then the shape, if you think about negative being a reflection across the x-axis, as we found in our transformation section, the graph is going to look something like this. Okay, so now as x approaches negative infinity, the function also approaches negative infinity, and as x approaches positive infinity, once again, the limit is negative infinity. It just keeps going down forever. Okay. All right, now let's examine functions of odd degree. Sorry. For example, a cubic type function, which in general looks like this. All right, now the limit of f of x as x goes to negative infinity is now negative infinity. It goes down forever. While as x approaches positive infinity, the function approaches positive infinity. Just keeps on going up like that. If we now take a negative leading coefficient, okay, once again it's a reflection, so it looks like this. And the limit as x approaches negative infinity is now positive infinity. And the limit of the function as x approaches positive infinity is negative infinity. Okay, so see, these are some things to keep in mind when we're working in this section. Another thing we need to think about is the extrema, okay, or the turning points. Now, I'm just going to say this. A polynomial of degree n has at most n minus 1 turning points. Okay, so if you think about a quadratic function, a function of x squared type, which looks like this, this is of degree 2, right, x squared, and it has one turning point right there. It the function is going down and then it's going up. So it turns once. Okay, in a polynomial of degree 3, okay, of degree 3, a cubic type function looks like this. The degree is 3, and it has two turning points. Right there and right there. So a polynomial of degree 2 has one turning point. Polynomial of degree 3 has two turning points. So a polynomial of degree n has at most n minus 1 turning points. At most. It can have fewer, but at most it has n minus 1. Okay, now let's talk about zeros. It can be shown that a polynomial of degree n has at most n zeros, or n roots, n real roots. Okay, some roots can be imaginary, so you might think that it has fewer than n roots, but it has at most n real zeros. Okay, so if we're talking about a polynomial, a parabola here, the roots are where it crosses the x-axis, and that's 2. So this is an x squared function, and it has 2 roots. A cubic type function has 3 roots, there, there, and there. All right, so it can have at most 3 real roots in this case, or of degree n real roots. And we're not going to deal with complex roots in this section, just real roots. Now, multiplicity. A factor's multiplicity is the number of times the factor occurs within the polynomial. For example, if we have this function, okay, we have, if I make a little table here of the factor and its multiplicity, we have a factor, the factors in here are 0, 3, -1, and +7, or the roots, or the zeros. You can call these any of those things, okay? So the factors, 0, 3, -1, and +7, those are the factors, or the roots, and their multiplicity is the number of times the factor occurs. So x is squared, so this is like x times x, so this factor appears twice. X minus 3, this factor, this is only to the first power, so that only occurs once. This one is to the 5th power, so it could be x minus 1 times x minus 1 times x minus 1, etc. So this one appears 5 times, and then this factor appears 4 times. So the multiplicity of the factor x equals 0 is 2, of the factor 3 is 1, of the factor 3 is -1, -1 is 5, and of the factor 7, the multiplicity is 4. Other factors to consider. Okay, let's say we have this function, which when I plotted it in Desmos turned out to be here. Okay, the factors being x equals 0, so the root touches the x-axis there. X equals 3, the function touches the x-axis there. -1 is the 0 here, and x equals 7 is the root there. Okay, so those are the factors of the roots. And what we can say about this is for factors that have even multiplicity, the graph is tangent to the x-axis at the corresponding 0. And when we say tangent, it means it just touches the axis. It doesn't cross it. It just touches it and goes back. Touches it and goes back. So the factors that have even multiplicity, x equals 0 has a multiplicity of 2, x equals 7 has a multiplicity of 4. If it's even multiplicity, then the graph is tangent to the axis at the corresponding 0. Okay, that is, it touches it and goes back. On the other hand, if it has odd multiplicity, it then crosses the x-axis at the corresponding 0. Note that at x equals -1, it crosses the axis. At x equals 3, it crosses the axis. Okay, so factors that have odd multiplicity, such as x equals 3 and x equals -1, it crosses the axis at those zeros. Example 2. Let's take this function and answer various questions. For example, how does the graph behave with relation to the x-axis at x equals 2? Well, notice the factor x equals 2 has a multiplicity of 2. And from the previous slide's information, we know that then the graph is tangent to the axis at x equals 2 because it has a multiplicity, because it has an even multiplicity. Part B, what are the real zeros of the function? Well, we could set the function equal to 0 and solve, and we would get this. And I think we could, if we separate and solve, we can see that the zeros are going to be -3, +2, and +5. So those are going to be the zeros here. What is the degree of the function? Well, if we ignore all the numbers and just write factors of x, we have x to the first power, x to the second power, x to the third power, which adds up to x to the sixth power. So therefore, the degree is 6. Now we have that information summarized nicely here. Next, we want to, what do we want to do next? We want to describe the end behavior using limit notation. Notice that it is a polynomial of degree 6, an even degree, and it has a negative leading coefficient. Okay, now if you look back a couple of slides, that leads to the end behavior looking like this. The limit of the function as x approaches -infinity is -infinity, and the limit of the function as x approaches +infinity is also -infinity. So that gives us the end behavior. Okay, now we're in a position to sketch a possible graph. First, let's plot the zeros. So there's a 0 at -3, there's a 0 at +2, and a 0 at +5. All right. Next, let's plot the end behavior. As x approaches -infinity, the function approaches -infinity. Okay. And as the function approaches +infinity, as x approaches +infinity, the function approaches -infinity. So that's the end behavior. Now let's look at the multiplicity and what the function does at the zeros. Since -3 is of odd degree and 5 is of odd degree also, we know it goes through the axis at those zeros. So it does something like that. And then at x equals 2, it has even multiplicity, so therefore it's going to be tangent to the axis. So it's going to look something like that. So from these characteristics, we can sketch a possible graph. All right, well, I went and plotted this in Desmos to see how the real graph would compare to my prediction, and it looked like that, which was pretty good. You know, it had zeros at -3, 2, and 5, just like mine did. It went through the axis at -3 and +5, and it was tangent at 2. Okay. The extrema, where the extrema are located, you'll find out how to do that. You know, the values of the function, where the extrema are in terms of the x value, and what the f of x value is. You'll find out that in calculus. So actually learn how to locate the x values of the extrema. That will be in your calculus class. Okay. Here we're just getting an approximation. All right, now, given this graph, let's write a possible function. So first of all, I want to make a box, and I'm going to just find the zeros. Now the zeros I locate at -6, at 0, and at 5. Okay, and then I look what the graph does at those values. Okay, and I can see that it's tangent at x equals -6. That leads me to believe that the multiplicity is even. I'll just call it 2. At x equals 0, it is also tangent. That leads me to also even multiplicity. And at x equals 5, it crosses the axis. It goes through the axis. So that leads me to a multiplicity of 1. All right, now adding those multiplicities, 2 and 2 and 1, I get odd. So I know the degree is odd, and I can just look at the graph too. And this reminded me of a cubic graph with a few bumps in between. Okay, so that's going to be of odd degree. All right, and because it's shaped like this, okay, so the end behavior matches up with one that has a positive leading coefficient. So I know that the leading coefficient is positive by the general shape of the given graph as compared to our known ones. And so now I can write a possible function as this. Okay, I have a 0 there, a 0 of -6 is contained there, and a 0 of 5 is contained there, and of the proper multiplicities. Okay. And then I went into Desmos just to check this, and I plotted this graph in Desmos, and there's what it looks like, which matches up pretty favorably with the given function. Okay. All right. Finally, we're going to factor this function and sketch a possible graph from this. Okay, this is going to take a little while to do. All right. First of all, we have to factor this to find the zeros. And so, first of all, I noticed that there's an x term. There's an x in every term. So I'm going to factor out an x. Okay. And when setting that equal to 0, that means that x is a 0. That x equals 0 is a 0. So we have one of them already. And then we're going to find the other ones by synthetic substitution or synthetic division. Now the possible factors are all the factors of, if I'm just focusing on the degree 4 function within the parentheses, okay, I don't have to think about this x anymore because we already have that determined out here. So I can just worry about the degree 4 function here, the degree 4 part here. And it has factors of -128 because the the leading coefficient, the x to the fourth coefficient is 1, right? So I don't have to worry about that. So it's negative 128. So I list all those and I get these. And I have to test these to see which are going to give me a remainder of 0, or which will indicate a 0. So we set this up like that with the coefficients 1, 6, negative 8, negative 6, negative 96, negative 128, and I just start picking one. So I'm going to pick positive 1. All right, so then bring the 1 down to get 1, multiply to get 1, add to get 7, multiply to get 7, add to get negative 1, multiply to get negative 1, add to negative 97, multiply to get negative 97, and it adds to that. So I know that doesn't work. Okay, that one doesn't work. So pick another one. I'm just going to pick negative 1 this time. And so going to the business here, negative 6 and negative 1 is 5, multiply to get negative 5, add to get negative 13, positive 13, add to get a negative 109, 109, kind of close, but nope, that one doesn't work either. Okay. All right, keep on trying. So I'm going to try 2 this time. So bring the 2 down, bring the 1 down, multiply to get 2, plus 6 is 8, times 2 is 16, plus negative 8 is 8, times 2 is 16, plus negative 96 is negative 80, negative 160, and no, that's way off. So that one doesn't work. All right, keep on working. So negative 2. So let's see. 1 times negative 2 is negative 2, plus 6 is 4, times negative 2 is negative 8, plus that is negative 16, multiply by negative 2 to get 32, add to negative 96 and get negative 64, times 2 is positive 100. Oh, hey, check that out. I get 0. Yay. So that means that negative 2 is a 0. Yay, I found another one. Okay, so we have x equals 0 is a 0. We have x equals negative 2 is a 0. Now the leftover polynomial here is 1 degree less from x to the 4th. So that's going to be 1x to the 3rd plus 4x squared minus 16x minus 64. And I have to continue to factor this. So I'm going to set that equal to 0. And gee, I wonder if can I factor this by grouping? I could continue to do this by synthetic substitution, but I think I can factor this by grouping. I think because I can pull an x squared out of the first term to get x plus 4, and I can pull a negative 16 out of the second two terms to get x plus 4, and then I can factor out the x plus 4, and I get this quantity x squared minus 16 times x plus 4. And then I noticed that the x squared minus 16 is a difference of 2 perfect squares. So I can factor that into quantity x plus 4 times quantity x minus 4. And then bring the previous x plus 4 along. And I get that, which I set equal to 0. And now I can see the other zeros are negative 4 from the first, positive 4 from the second, negative 4 again from the third. And so the zeros are negative 4 and 4. The negative 4 happens twice, actually. So the original polynomial can be factored into these binomials. Okay, x equals 0 was a 0, x equals negative 2 was a 0, and then what we have in this line right here is right there. Writing this a little bit differently, you get that. Okay, so the original polynomial can be factored into this. Which we can now glean information from. We know the zeros, and now we can find their multiplicities. At x equals 0, multiplicity is 1. At x equals negative 2, the multiplicity is 1. At x equals negative 4, the multiplicity is 2. And at x equals 4, the multiplicity is 1. Okay. Adding up those multiplicities, we get 5, which makes sense because the original polynomial is of degree 5. And we can see that it has a positive leading coefficient. In this case, positive 1. So the general shape of the graph is going to look like this. Okay. We know the end behavior now. The end behavior is as x goes to negative infinity, the function goes to negative infinity, and as x goes to positive infinity, the function goes to positive infinity. So it's going to be of this general shape. Okay, so let's plot this. We're going to plot the zeros first. So there's my zeros. -4, -2, 0, and 4. There's the end behavior. Okay, similar to the kind of graph up here as a visual. And now at -4, it has multiplicity of 2. So it's going to be tangent there. At x equals -2, has a multiplicity of 1. It's going to go through. At x equals 0, it has multiplicity of 1. It's going to go through. And at x equals 4, it has a multiplicity of 1. So it has to go through, which makes sense because you have to have that end match up to that end. So we get this. And so there is a possible graph for this function. Okay? And just for fun, I checked that by plotting the function in Desmos, and here's what it was. And I can see that it matches up pretty favorably with my prediction. So by knowing a little bit about multiplicities and end behaviors and factoring, we can get the general shape of a graph from the polynomial function. Okay, takes a bit of work, but it certainly can be done. And once again, later in your when you take actual calculus, you'll be able to get this more precise by knowing where the extrema are and where the values of the function at those extrema are, and so forth and so on. So it'll be more accurate. But you get a pretty good approximation using pre-calculus principles. Okay, time for some practice problems.